Imaginary and complex numbers video number 2. On this video, we will cover simplifying expressions that involve imaginary numbers and complex numbers. We will also cover stating the complex conjugate of any complex number. And if we have time, we will be able to get to graphing complex numbers on a complex plane, but I'm not too sure if we're actually going to get to that. So let's go to this next slide. We have lots of problems here that have imaginary numbers, right? What are imaginary numbers? 3i is an imaginary number, 2i is an imaginary number. Right here, 3i plus 2, this part's imaginary, this part's real. We'll get to that in a little while, but we wouldn't call this an imaginary number if we're looking at the whole thing as a binomial. Let's start with number 1. Simplifying imaginary numbers is kind of like simplifying a number with a variable in it, right? It's kind of like if you had a 3x times a 2x. What's the answer? It's 6x squared. In this case, 6i squared. But we know from the past that I squared equals -1, so what we really have is 6 times -1, which is -6 as your final answer. So what I'm going to do is just move it over a little more, and we're going to get -6 as our final answer for number 1. Number 2, we have 3i plus 2i. That's just combining like terms. What's 3i plus 2i? It's 5i. I mean, the I is truly a variable, like X or like Y or like Z. You're just combining like terms right there. 3i plus 2i is 5i. How about 3i plus 2? Well, that's kind of like having a number with a variable and then just a number. You cannot add 3i plus 2. You can't add 3x plus 2. You can't add 3y plus 2. So you cannot add 3i plus 2. So I'm just going to rewrite it. But let's put it in the correct form. Remember, not conjugates, complex numbers have two parts. They have the real part first, so that's the real part 2, and the imaginary part second. So this is the correct way to write that binomial. Not 3i plus 2, but 2 plus 3i. Number 4, what are we doing here? We are distributing 2i times 3. That's going to be 6i. How about 2i times -2i? That's going to be a -4i squared. Okay. Now, what else could we do there? Well, we know that I squared is really -1, right? That's something that we need to know. I squared is -1, so we have an I squared right here, so that's really a -1. So my new problem is going to be 6i minus 4 times -1, which means that you'll have 6i plus 4, which means that you want to rewrite it in the correct form of a complex number, and that would mean that you put your real part first and your imaginary part second. So there's your answer to number 4. 4 plus 6i. And let's move on to number 5. And let me make this all smaller. Push it to the side, and let's just focus in on 5. 5 right here, you want to, just like radicals, you don't want to have a radical in the denominator. Right here, you don't want an imaginary in the denominator, an imaginary number. So what you could do is simply multiply by I, both top and bottom, by I. That way on top you get 3i, and on the bottom you get 2i squared. Now what's the purpose of multiplying I times I? To get the I squared, because we know that I squared is really -1. So you really have 3i over 2 times -1, which means that you have, let me write it over here, equals 3i over -2. And again, you don't want to leave a negative in the denominator. Let's just either move it to the center or move it all the way up, whatever you want. I'm going to move it just to the center, make it -3i over 2. That's my final answer for number 5. So remember, just like radicals, you don't want a radical in the denominator. You don't want an imaginary value in the denominator either. Let's move on to something more challenging, like if you had a complex number in the denominator instead of just an imaginary number in the denominator. So right here, we have examples where I don't just have an imaginary number in the denominator, I actually have a complex number in the denominator. Again, what's the difference between imaginary? Imaginary is just when you have something like 3i. That's an imaginary number. But if you ever have something like 2 plus 3i, then it's no longer just imaginary. It has a real part to it, and it has an imaginary part to it, and that makes it a complex number. That's what a complex number is. It's a binomial where your first part's the real part and your second part's the imaginary part. So what I want to do right now is recognize that I do not want this I in the denominator, and just like I don't want square roots in the denominator, if you do have a binomial, you can't just get rid of the I by multiplying by I. It doesn't work anymore because you have a binomial, and the only way to get rid of the binomial that involves the I is to multiply by its complex conjugate. Now, we've already dealt with conjugates before. It's the same exact thing. The only thing that we're doing is throwing the word complex in front of it. So if you do 3 minus I, both on top and bottom, you will see that the imaginary values, actually the complex number completely disappears. You end up with a regular number. Kind of like when we multiplied by the conjugate when you had a radical in the denominator. It got rid of the radical. Right here, it'll get rid of the imaginary number. So let's actually work this out. Yeah, let me zoom in a little so we can show this nice and clear. 6 times 3 is 18, and then 6 times I is negative 6i. And then on the bottom, I want to go 3 times 3, that's going to give me a 9, and then 3 times negative I, that's going to give me a negative 3i, and a positive I times 3, that's going to give me a positive 3i, and last but not least, the positive I times a negative I, that's going to give me a negative I squared. Okay. Once again, the middle terms are complete opposites, so the minus 3i and the plus 3i cancel out. And once again, you have an I squared, and an I squared is really a negative 1. So what I really have, let me move this to the side, what I really have is 9 minus a negative 1, because I squared is really a negative 1. And this is all in the denominator. So what I really have is 10 in the denominator. So my top is 18 minus 6i, and on the bottom I do have 10. So this is my answer so far. The question is there anything else that I could do? Well, all three numbers are even numbers, so I could at least reduce by 2. So if I reduce by 2, I'll get a 9 right here, I'll get a 3 right here, and I'll get a 5 down here. So let me rewrite it. Here it is. We have 9 minus 3i over 5. That's my answer. But one more detail, because it's a complex number, you don't want to leave it both parts. You don't want to leave both parts together over one number. You actually want to separate the real part being first and the imaginary part being second. So you probably want to go 9 over 5 minus 3 over 5 with an I. That would be the best answer. I mean, the top one works, but the bottom one really is the best. Let's move on to number 2. Number 2, this is definitely a lot more challenging because you have a complex number up on top and a complex number on the bottom. So again, who cares about imaginary being in the numerator? That's fine. The problem is having an imaginary in the denominator. Now, because this is a complex number, which is a binomial, a real part, imaginary part, we're going to get rid of it by multiplying it by its complex conjugate. The complex conjugate will simply be 5 minus 9i. And what you do to the bottom, you must do to the top, 5 minus 9i. And we're going to distribute. Let's do the top first. So I have this binomial up on top, which is a complex number also. If I go negative 1 times 5, I want to get negative 5. If I go negative 1 times negative 9i, I want to get a positive 9i. And if I go negative 6i times 5, it's going to give me a negative 30i. And if I go negative 6i times negative 9, that's going to give me a positive 54i squared. Okay? Now on the top I could still simplify. I'm going to combine the like terms, the I values, I minus 30i. That'll give me a negative 21i. And the 5 comes down, that negative 5 comes down. And what else? I have a 54i squared. That's really going to be a 54. I squared is really a negative 1. So I really have a 54 times negative 1. So what do I really have on the top? On the top I have the negative 21i, which I want to write second because I want my imaginary part second. And I have negative 54 minus 5. Negative 54 minus 5 is going to be a negative 59. So I have negative 59 minus 21i. And that is the numerator. Okay, now for the denominator. Let's go with 5 times 5, that's 25. 5 times negative 9i, that's negative 45i. Positive 9i times 5, that's positive 45i. Positive 9i times negative 9i, that's negative 81i squared. And the middle terms always cancel out. They're both opposite values, so I have 25 minus 81, but times a negative 1. So it's not going to really be negative 81 minus, or negative 81 times negative 1. It's going to be 25 plus 81. And 25 plus 81 is 106. So the denominator is 106. So far, that's our answer. Let's see if we could actually reduce, maybe by 3. And I just tried to reduce it, and I wasn't able to with the calculator. So what I'm going to do is just separate it, and my final answer will be negative 59 over 106 minus 21 over 106, but this second term is an I term. So it doesn't look like we're going to have much time to graph. I'll have to do another video on graphing complex numbers on a complex plane. But we could do a couple more algebra tricks with complex numbers. So as you can see here, we have a complex number times its conjugate. That'll always make the imaginary parts disappear and just have a real number. So when I distribute, 3 times 3 is 9. 3 times negative 2i is negative 6i. 2 times 3, or 2i times 3 is positive 6i. Positive 2i times negative 2i is negative 4i squared. And of course the negative 4i squared is really a negative 4 times negative 1. And of course the middle terms cancel out. So you really have 9 and the negative 4 times negative 1. So you really have 9 plus 4, which is 13. Super easy. Let's just do one more, and we could just do any type of randomness, like how about, let's go 3i times 2 minus 5i, take away 8i, I don't know, something like that. It's just regular algebra, guys. When you go 3i times 2, it's going to be a 6i. And you go 3i times negative 5i, that's a negative 15i squared. Then you bring down the minus 8i. And of course, you could combine this first I with that last I, and it'll give you a negative 3i. And what about the negative 15i squared? We know I squared is negative 1, so I really have negative 15 times negative 1, which means I do have a positive 15 minus 3i. And that would be my answer right there, that complex number. I hope we get this, guys.